什么时候有时间可以讨论 poster 啊？对啊，下课再因为今天我现在不要讨论这事情啊。一般我上课之前比较不喜欢讨论别的事情啊。今天这有会录影吗？哦，好，OK，好。Okay. All right. So welcome back to DSP. So today I'd like to, as you are now looking at, this is your midterm number 2. So I plan to briefly go through all the questions. Yesterday it took myself 80 minutes to finish writing. So I realized that even for myself, it took me 80 minutes to finish writing the answer that I already know. so don't feel too bad if you cannot finish in time. Right. All right. But anyway, so let's start with number 1. Okay, we do have a few places that I have been discussing with the TA. So there are a few definitions that may lead to confusion. So we decided that maybe in certain situations you may be able to argue that we need to give you credit. Okay, so I promise we'll touch that. Yeah. So we are going to touch on that. But otherwise, let's start with the first question. Okay? The first question is all about group delay. Okay, all about group delay. And A part, I'm asking you to give a general condition for an FIR filter so that the filter gives a constant group delay of 10 samples for all frequencies. And the key concept that we are looking for, we want you to answer is symmetry. The key concept really is symmetry. So I expect that the correct answer would, if you want to answer concisely, you need to point out that, for example, with this even symmetry, if the impulse response is evenly symmetric around the midpoint, then we can show, then the following derivation will show you that the group delay is constant. Why? Let's proceed. If H has this even symmetry in between time 0 and 20, and it's FIR, right? So we can just easily assume that elsewhere, outside this range, Hn is 0. It has a finite impulse response. And then the first step involves moving H to the left by 10 sample. The midpoint is now 10. But after moving to the left, note that this is shifted to the left, then G becomes what we call zero phase. G becomes non-causal, but otherwise zero phase meaning that you can show that if when G is moved to the left, you can show quickly that G minus n equals to Gn. G is an even function. Okay? G becomes an even function so that we know that its Fourier transform is real, meaning that the phase is basically the slope of phase for any real number, real spectrum, the slope is all zero. Slope is all zero. So meaning that now, if G is real, then back to H, if we consider H being G shifted to the right. H, now it is, since we know that it is G shifted to the right, therefore H, the spectrum of H is the spectrum of G multiplied with a linear phase term. And since this part is real, so we consider the slope of the phase spectrum is going to be just taking the slope of this term, which is exactly 10, and the unit is samples. So this is kind of the concept I'm looking for. The key concept is symmetry. Okay. So that's A part. And B part, the next part, what would be a sufficient condition? Okay, sufficient condition for an IR filter to have positive group delay for all frequencies. So, again, a bit about what does a sufficient condition mean? Sufficient means that if this condition holds, then this IR filter is guaranteed to have positive group delay for all frequencies. Okay, so that's why it means what a sufficient condition means. Otherwise, the opposite is necessary condition. So if the way you answer the question is suppose is to begin by assuming an IR filter have positive group delay for all frequencies. If you start from there, then any conclusion you reach is a necessary condition. So that's exactly the opposite direction. Okay, so we're talking about mathematical logic, right? So I discussed with the TA. So they found that some of you answered the other way around. So that's not what I mean here. So what would be one sufficient condition for an IR filter? I was testing you that you remember all-pass filter has this property. Okay, in our homework 5.3c, we talked about an all-pass filter is a sufficient condition because any all-pass filter always has positive group delay for all omega, right? So you can simply answer that. You just say, for example, an all-pass filter satisfies this property. That should give you full score. Okay. Any comments so far? Yeah. Any comment from the TAs? No, not really.
Just write all-pass filter out.
All-pass filter. So all right. And the C part, I'm asking: is it possible to have a causal filter to have a negative group delay at certain frequency? This is a kind of a this could be a deep question. Okay, but for those of you that happen to recall to have prepared that in lecture 7, if you remember, there is a plot like this. At that time, we were discussing this system. For this very system, its phase response has a negative slope at first, and then it becomes positive. But this system is a causal system, right? So that's so the answer is yes, it is possible, right? The answer is yes. Okay, so and this is counterintuitive. Okay, so if you ask why, or there seems to be a contradiction, right? Causal, meaning that you cause and effect, everything output should follow the input, right? But how come the group delay could be negative? So that's actually a pretty deep question, right? But I agree, this is a deep question. But the short answer is yes, and this is an example. Right? This is example that's from lecture number 7. Right. So that's that's question number 1, right? Turns out that nobody get the full 15 points. Nobody in this class, right? So anyway, this is pretty tricky. A group delay could be a deep concept, right? So let me explain why a causal filter can have a negative group delay at certain frequencies. Okay, so the idea is that for some filters, some systems, some causal system can perform cancellation. Cancellation. Have you heard about echo cancellation, noise cancellation, such kind of things? Your smart earphone, some of them performs cancels outside noise from outside. Okay, so what happens is that the filter, the system, it's a causal system, but for an input at certain frequencies, let's say we receive a packet like that, so that's the input. So a system could be able to cancel the input after it looks at a few samples. Okay, let me say that again. A system can cancel the input after it looks at a few samples. So everything comes afterward. Everything, indeed, comes after we receive the input. But what could happen is that for such kind of system, then because it looks at a few samples and then you figure out the frequency is, I'm going to cancel. I'm going to cancel the rest. So the input is like this, but the output becomes smaller, and it is soon canceled after seeing a few samples. Okay, and this system, is it causal? Yeah, we can construct a system like that. That performs cancellation. Okay, we can cancel the signal as long as it's near certain frequency range. Such kind of system exists, right? And for this kind of system, everything's still causal. So we don't produce any output even before the system receives any input. Okay, so that's not happening. Everything happens after time zero. Everything happens after time zero. But yet, when you consider group delay, what's the meaning of group delay? Group delay is also called energy delay, right? So group delay tells you the latency from the kind of centroid of the input to the centroid of the output. So in this case, the delay is going backward. Okay, so delay could be negative, even though everything the system is causal. It doesn't violate special relativity or anything like that. So nothing's violated. So this is possible. Okay, so essentially that's what's happening right here in this frequency range. Okay, right. Okay. Okay, so that's question number one. Now, can I move on to question number two? Do our TAs have any comments? What did you observe?
In 1C, there's a lot of people wouldn't tell me like what kind of system are you in right now, but then just directly tell me that there will exist some. Just give me like the plot of a phase and tell me like there will exist this kind of system.
Okay, yeah.
I wouldn't give you the point for this because like.
So you just
agree.
discarded all. They got zero.
Not
Do they get zero?
they got partial points.
Partial points. Yeah, I think partial is fine. Yeah, because at least you're showing that you know the definition of negative group delay. Yeah, I think it can. Partial credit is all right. Yeah, but probably in this case, is it possible? Right. The best answer is to just give an example. That's the safest. Okay. So, but anyway, I want to kind of share with you that this is possible. It's an interesting question. All right. So, should I move on to question number two? Okay, yeah. Question number two is all about calculation. Okay. So, question number two, for this part, we handle rectangular window and which window? The Hahn window. First in continuous time domain, and in the last part, I asked you to draw the magnitude spectrum after we sample the continuous time window. So the first part, I'm asking you that we know that the window, if you have learned this, we know that the window should, after taking the Fourier transform, the window should look like it's a sinc function. It's still a sinc function. So I'm asking you to find the equation for extremium to happen. So we know that for any function to reach its maximum, local maximum or minimum, you take the first derivative, right? 微分一次嘛. So you take the first derivative, so that's exactly what we're going to do. We just take the derivative of r of omega, okay, which is given to you. We have given to you that r of omega looks like this, which is a sinc function. Actually, I missed the subscript c. Take the first derivative, and this is just a basic calculus. And you'll see that for the top to become 0, this needs to happen. So that after some rearrangement, you'll see that you have proved that the condition is what's listed right here. This is the condition for the first derivative to become 0, to vanish. Become 0. Vanish 就是变成零，消失。Okay, so that's part A. And part B, continuing from here. So if you take a closer look, unfortunately, maybe in the test you have some pressure, time pressure, right? But if you now look back and contemplate on this equation is a transcendental equation. 超越方程式, transcendental equation, meaning that the solution has no closed form. Okay, so just as a kind of extra sharing. So we want to find out when does n omega equal to tangent n omega. So tangent look like this, right? Tangent function is a periodic function which repeats itself every pi, with a period of pi. Okay, so that's tangent of theta. So we are asking, when does theta equal to tangent theta? Right? Essentially, that's what we are going to look at, right? And the answer is we look at the intersection of two functions, right? So 0 is the first place that they become equal. Otherwise, the second place should be somewhere right here, and so on. The third place could be, let me draw another copy of tangent. The third place is somewhere right there. 1, 2, 3, and so on. So that's why I reach a kind of approximation that so we can name these zero crossing by, this is the first frequency, omega 1, this is omega 2, and so on. So they, as n approaches infinity, we'll find that the frequency at which this equation, the equality holds, approaches, they are going to be spaced almost, they are going to be spaced equally, at equal interval in between, okay, in the frequency domain, along the frequency axis. So there is a kind of approximated expression for the zero crossings, for the extrema to occur. And that's going to be n plus, that's going to be a half integer multiple of pi divided by big N. Big N being the length of the window, the rectangular window. This is not the most interesting part, but so anyway, I proceeded to ask you to calculate a few of them. Okay, calculate the Fourier transform at this half integer multiple of pi divided by n. 2/3, not 2/3, 3/2 2/3 3/2 or 5/2 1.5 times or 2.5 times pi divided by n. Because what are they going to tell you? They're going to tell you the height of the side lobe, essentially. Local maximum, right? Local minimum being negative. They are going to tell you, these numbers are going to tell us the height of the side lobes for the rectangular window. So if you just follow some quick calculation, just plug into the original expression right there, you find that at 3 divided by 2, at that place, the answer is that. And at 2.5 times pi divided by n, the answer becomes that. So just a quick observation, you can be sure that there is an inverse proportional relationship, 反比. Why? Because we have omega in the denominator. Because we have omega in the denominator somewhere right here. That's the very reason. That's the very reason we have an inverse proportional relationship. Okay, when sine n pi becomes plus or minus 1. Approximately, that's where the local maximum or minimum occur. Okay. So no wonder we have 3 pi here, 5 pi here. And similarly, you can keep on. You can keep on going, and you find that you push further to the right along the frequency axis, 7 here, 7 here. There is an inverse proportional relationship, and we will need this actually. We will need this. Okay, but this part is just pretty straightforward calculation. It takes time, but it's pretty straightforward. Hopefully. And now moving on to C part, we need the result from the previous step. Okay, in C part, we tell you again that we have discussed in class in one of the discussion sessions that when we now consider the Han window, which can be written as rectangular window multiplied by 1/2 plus 1/2 cosine something, cosine t. So we've shown in class that the spectrum of the Fourier transform of a continuous time Han window equals to that of the rectangular window plus the rectangular window's Fourier transform shifted to the right and shifted to the left. There is a linear combination of coefficients are 1/2, 1/4, and 1/4. Right? This is something we have shown during the discussion session, during one of the discussion sessions. Right? Now, just apply this. Now, I ask you to calculate the superposition of those three functions with the correct linear combination coefficient. 1/2 right here, 1/4 right here, 1/4 right there. I'm coding them in different colors. Please take a look. Just intentionally, I show them the three components by three colors. Okay, so essentially, we are trying to superpose them and calculate what the sum is right at which frequency? Right at 2.5 times the half width of the main lobe. Okay, which is pi divided by n. So here on my reference solution, note that my frequency axis on this plot is omega divided in the unit of pi divided by n. Okay, and we are asking you to calculate the value exactly at 2.5 times that. That's right here. So right here is a quick calculation. We're going to have extract. There is going to be a factor of n divided by pi when we calculate it, and 1/2 times 4n divided by 5, 1/4 times 4n divided by 3, 1/4 times 4n divided by 7. That's exactly what's going on. Superposition of three things. The biggest thing right here, itself shifted to the right and itself shifted to the left. All superposed in the frequency domain right here. That's what's going on. And why? Because that location is approximately going to be where you see the first side lobe for the Han window. Okay, that's kind of the beauty of cosine family of windows. Right? You know exactly. You can find very good approximation of where the height, the local maximum occurs in the Fourier transform. That's the beauty. They occur at n plus one half times something, right? Almost equally spaced. So with that, really, 2 divided by 5, okay, just after some simple algebra, you find the answer is that, okay? Now the answer is that. And when we move on to the next question, which follows this part, in the next question, finally we introduce sampling, because so far we talked about continuous time windows. But this course is mainly about digital, okay, about discrete time. So now after sampling the window function in the time domain with a sampling period of 1, you can show that now I specify that big N, okay, the length is 20. The length is 20, so the result should be when you so I try to break this into 2 steps, okay? First, in this plot, I'm emphasizing that after sampling, we have aliasing. We have repeated copy of the spectrum in the frequency domain. Okay, so you can tell me that there will be aliasing. Sure, that's correct. Okay, so I'm emphasizing that now we have one copy of the sinc function, another copy of the sinc function, which is 2 pi away. The distance is 2 pi. Okay, from the first copy, and theoretically they are going to interfere with each other. All these copies of sinc functions are going to interfere with each other, but probably when they are sufficiently far away, the interference hopefully can be negligible. That's the idea. Okay, that's the idea. So so what did I write down? So let me go through. Since W is the continuous window sampled with a sampling period 1, so just roughly speaking, this is DTFT. The DTFT of the Han window is going to be formulated by an infinite sum of the good old continuous time Fourier transform of the Han window, but repeatedly occurring at integer motive of 2 pi. Okay, they're going to sum up. They're going to sum up. So here I put an approximation right here. I say, I claim that if we look at the first silo, the highest silo, right? The first silo, which should happen at approximately 2.5 times pi divided by n, where n is 20. So if you just plug that in, is that correct? 2.5, yeah. So you find that you need to evaluate W. You need to evaluate W at this frequency, this digital frequency. Okay, small omega right there. Yeah. And the answer still just should be approximately same as what you obtained from the previous this is the previous part. Okay, approximately, and so here I'm being really sloppy. Sometimes I encourage you to become sloppy. So here, so look, yeah. So I suggest that if you without calculator, it turns out that if you observe your answer, it's going to be 32 minus 32 divided by 21 pi, right? So to me, I'm being sloppy in that 32 is roughly 10 pi, right? That's kind of sloppy, but I encourage you to do that, yeah, to do the same. 32, if 32 is roughly 10 pi, and 21 is roughly 20, right? Oh. So we can drink at the age of 21 or 20, roughly speaking, when you are in America. Don't quote on me. 20岁或 I encourage you to do this stupid approximation. It's stupid, but it's helpful. Right? It helps you to figure out that 20 log of that is roughly minus 6. Okay, so to make a sketch, you're asked when you are asked to make a sketch, I would do it. Okay, when I'm asked to make a sketch without using a calculator, I would do this. I would totally do this. Okay, so if you just plot it, and we know that what is 26? 26 is 20 log 20. Okay, now dB, the definition of dB is 20 log magnitude. Okay, or 10 log 10 energy. Okay, so when this is magnitude, we need to multiply by 20. Okay, that's another detail, right? So 26 right here, minus 6. Now we following all the busy steps right here. Finally, we reach an approximation that we made a lot of approximation along the way. Okay, but in the end, we figure out maybe the main lobe to side lobe ratio is about 32 dB. Okay, so you can check against the textbook. The textbook, there is the correct answer. What is the correct answer? 31. Okay, we are off by 1. Big deal. So that will be my reference solution. You might be able to calculate exactly what is 32 divided by 21 pi. But I would totally do this. This is just how I would try to at least get some answer. Okay, this is kind of a back of envelope calculation. Have you heard of the term back of envelope calculation? It means that when you need to do a calculation and you only have an envelope, which is about this big, right? So how do you use that space to at least draw some approximation? Okay. So this is kind of an example of back of envelope calculation, right? So let me move on because of for time's sake. So let's move on to question number 3. Okay. Question number 3. We have the Kaiser family of window, and for the A part, I'm asking you to take a look of this figure and tell me if you have, when we have this spec peak approximation error being 0.001, and we have the transition with requirement that it needs to be no more than 0.05 times Nyquist frequency. So first of all, let me clarify, Nyquist frequency, in most of my lectures, Nyquist frequencies means sampling frequency divided by 2, okay, in most, but unfortunately not all. So I apologize. I apologize if this is your confusion. I apologize. We need to give you some credit. Okay. So some of you wrote down. I learned from TA. TA told me that some of you define Nyquist frequency as the highest frequency in an analog signal. Did some of you do that in this classroom? Later we checked with the textbook. Okay, there really was a place in the textbook that defined Nyquist frequency like that. So that's a kind of there's a discrepancy in the definition of Nyquist frequency. So if you use that definition, then you're in trouble because you cannot solve this. Okay, so I apologize because at one point in my lecture I also used that definition early on when we were in chapter 4. Okay, I also used that definition one time, maybe at that time, so a few months ago. So I apologize. So if this is your confusion, please come to the TA. We give you some more credits. Okay, but otherwise, if you see Nyquist frequency as basically not this, basically pi. Pi represents the Nyquist frequency. Okay, half of sampling rate. Then so first step first, okay? So first, we ask you to find beta and m. So beta can be directly inferred from here because 0.001 is 60 dB, is minus 60 dB, right? So here I'm looking for you to understand that you can simply pull a straight line right here. Just extend the straight line and see how minus 60, where it corresponds to this point right there, right? And this point right there is in between Kaiser 6 and Kaiser 5. It's in between Kaiser 6 and Kaiser 5. So just by inspection, by Kaiser 6 right here, Kaiser 5 right there. That's the way we read this plot. So in between, so I'm going to guess this is probably something like from between 5 and 6. This is like 5.6, okay? Maybe 5.7. I say 5.6, okay? So I would just, this is the way I figure an approximate, a candidate solution. A candidate will, how about beta equals to 5.6? Why? Because it's before 5 and, between 5 and 6, okay? That's where I read this plot. And now, how about m? How about m? So we see that in this plot is m equals to 32, okay? Just know that the filter order is 32 for this plot, for this very plot. And we know that the transition width is going to be inversely proportional to the length of the filter. To the length of the filter. Okay, so I'm just going to suggest that if a m of 32 in this case reaches a transition, it gives you a transition width of roughly 0.23 pi. But now you are asked to fulfill this requirement that the transition width should be no more than 0.05. We can simply apply the inverse proportional relationship. Okay, simply apply that. We know that with 32 we can achieve this transition width. And now we need to shorten the transition width all the way to here. What should we do? We should lengthen the order of the filter, just inverse proportionally. Okay, so that the quick calculation will be inverse proportional to the transition width. With this calculation, 32 times about 4.6. I do my calculation right there. Okay. You get an answer. You can, for even fancy, put a ceiling right here. The answer is 1. So then I reach my guess. My guess is that's how I reach how I calculate a rough answer. Okay, you might do better than that, but I think yeah. So that's kind of the this is about reading the plot. Okay, using the plot. Okay. So hopefully you understand Kaiser, how we select the Kaiser order and the Kaiser parameter, okay, by reading this plot. Yeah. Any comment from the TAs?
If you use, some people actually use the equation from the textbook.
From the textbook, okay, yeah, which I didn't cover in class, yeah. There is a kind of numerical approximation suggested by the textbook, okay? So some people use that. So what's the answer? If you use that, what's the answer?
Yeah, they mostly still would be about 150.
About 150, okay? Again, my answer is not too much off from a better approximation, okay? Just merely by looking at the chart, right?
The exact answer would be a 145.
Oh, 145, okay, all right, how? So that's part A. For part B, I'm looking for a kind of complete disclosure of the filter design process in steps. Okay, so let's quickly get this. So we will begin with ideal low-pass filters impulse response. This is what is inverse Fourier transform. Okay, we covered this. It's going to be the sinc function in discrete time, and I asked you how the bandwidth, how the desired bandwidth would affect your result. So I'm not sure if some of you just bother to draw the sinc function with different cutoff frequency. The cutoff frequency shows up right here. Okay, your desired cutoff frequency, the bandwidth, shows up right here. So we can be sure that when we increase the bandwidth, the height is going to be taller, but the first zero crossing is going to get closer to 0. Okay, you have a narrower but taller peak in the middle. That's when omega, with increasing omega, you have a narrower but taller peak. And so the opposite direction, when we have a what? This is about decreasing omega. Okay, decreasing the cutoff frequency, you have the fatter and shorter peak at time 0. Okay, some of you call it this thing main lobe. Yeah, I'm not going to to say anything against that, but usually, let me just suggest. Usually, when we talk about main lobe, it's in the frequency domain, okay, or even in the space domain. Sometimes people talk about spatial Fourier transform in optics or acoustics. But here, it's the same function. It's the same sinc function. So I wouldn't call it a main lobe, but if you call it main lobe, I think it's fine. Right? I think it's fine. Right. So, but the key idea is that the cutoff frequency affects the height of in the middle, and it affects where you see the first zero crossing. Okay. But otherwise, so with any cutoff frequency, when the cutoff frequency is specified, you can plot the sinc and then apply the window function that you previously found with an appropriate beta and length m. Basically, you're going to apply window which ranges from time minus m divided by 2 to plus m divided by 2. Okay, there is a minus, should be a minus sign right here. Okay, and then truncate. For outside, we are going to truncate everything to 0. And this is going to be your filter, but the only problem is that this filter is non-causal, strictly speaking. 严格来讲, it's non-causal. So we need to further shift the filter to the right by exactly this amount, so that everything becomes causal, and that will be our final design. Okay. Okay. So let me move on to question number 4. In question number 4. This is a tricky question I came up with. It's a new question. So I was asking you to compare 2 different ways of designing an IR filter. The first way is sampling the analog response, which is lecture number 7. And the second way is bilinear transform, which is lecture number 8. So lecture number 7 versus lecture number 8. So I was asking you first to tell us what are the guidelines for choosing approximate parameters T and TD for bilinear transformation? T for the first method, TD for the second method. And so I would suggest that you can write down that we prefer T to be as short as we can afford, as short as possible, as short as reasonable. And lecture 8, TD, we had extended discussion in class and also previously. So if you just write down this equation, that basically is it, right? So that's part A. Okay. And part B is an open-ended question. Okay, so I'm asking you to suggest whether we can use the first method, sampling the analog response, using that method to design a Butterworth filter. My answer is yes. Please never say never. Right? Never say never. So I think it's doable. Okay, how doable? So I would. This is my thesis. Okay, 这是我的主张啊. My thesis will be, first, still begin with the prototype analog system with radius omega c and so on. Right? Butterworth filter and its Laplace transform look like that, with poles on the left-hand side of the S-plane. Okay, a few poles. I will draw a figure to help me explain, and then we know that this expression can be written in this form. So the idea is that some of you point out that the inverse Laplace transform might be difficult to obtain. Now, some of you pointed out that's good. Okay, so you don't absolutely need to go through my step. Okay, but it got to be possible to find out the inverse Laplace transform. That might be an obstacle, but it's doable. Okay, I think it's doable to derive the inverse Laplace transform. Why? Because we need to sample the impulse response in the time domain. That's the first method, right? So once you find out that the inverse Laplace transform, which is the impulse response of the system, then you can start sampling it by using this definition. Okay, so that's why I think it's doable, and we need to have a sufficiently small t. Okay, sample is fast enough. Then what are the advantages and drawbacks. Okay, here is my try. Okay, I argue that if t is small enough, then the frequency relation is linear. So basically, HC. So I argue that the advantage is that you keep basically a linear frequency relation. We have a linear frequency relation somewhere. Yeah. Right here. Oh. Right here. We have the advantage of omega being proportional to big omega. The frequency relation between big omega and small omega here is a linear one. Basically, big omega is small omega divided by t. Okay? And you may call that a merit, an advantage, a good property. Okay? But the good property is double-sided. The bad side is that because this prototype frequency response extends to infinity, so after sampling its impulse response, so back in the frequency domain, we should expect aliasing in the frequency response of our design. Okay, so there will be aliasing. This frequency response might suffer from some aliasing. So you might not be able to say that its magnitude monotonically decreases, for example. Recall that that's a nice property of bilinear transformation. Okay. So I will not give myself a full score. Okay, I promise. 这是假掰了，这我也不用考试。But anyway, so this is kind of something I would like to share with you. Okay. Any comment from our TAs? 关于这一题 about this question. Any comments you want to make right now?
Some people also say that we can make sure the sampled impulse response has the pole at the exact position as
Oh.
when doing bilinear transformation. So might be unstable.
That's a very good, very interesting point. I haven't thought about it, honestly. I haven't thought about the general condition when we apply the first method. Where are the poles going to be moved? Okay, yeah. So how many points did you give?
If they only write down that, only 5 or 6.
5 or 6 points, okay. Okay, yeah. All right, so anyway, as I said, this is an open-ended question. So please don't feel too bad. Research is always open-ended. So you're always, somebody will criticize you. Somebody will appreciate your research. Somebody will not. So please, hopefully, this is a kind of, I want this to provoke more thinking. Hopefully, this is my purpose. Okay. And finally, the last question is about a tricky way of designing a high-pass filter. I'm asking, can we just say we would obtain a high-pass filter by, can we say that a high-pass filter can be obtained by subtracting a low-pass impulse response from delta of n? Delta n being, by the way, delta of n, let's recall, delta of n is this thing. It's this one sample function, discrete time signal, okay? And we know that it's I'm making this suggestion, or I'm asking because we know that the first transform of delta of n is equal to 1 for all omega, okay? And the next thing, so now in this relation, we know that its spectrum is going to be 1 minus that of a low pass. 1, why? Because 1 is the first transform of the delta impulse. Okay? And here we're not talking about analog delta function. Okay, this is discrete time. Everything is already in discrete time. Okay, yeah. So after clarifying that, so the answer, short answer is for the first part, the answer is yes. Why? Because if we have a high pass and the frequency response is all real, this frequency response is all real, zero phase. It's an even function, really even function in the time domain. So again, frequency response is all real. So once, if that's the case, then one subtract by that is all real. And we know that the pass band becomes stop band, and the stop band becomes pass band. Basically, the polarity is inverted. Okay, now the function is inverted. 1 subtract by 0 is 1. 1 subtract by 1 is 0. That is as basic as that. Okay, so my answer to the first part is yes. Now the second part, unfortunately, is no. Why? Because even though the magnitude response has a pass band and stop band, but the problem is when we remove the absolute value here, there is a non-zero phase spectrum. Okay, so now therefore when we subtract 1 by the low pass, which is the first transform of this expression I was suggesting, unfortunately that wouldn't work. Because 1 subtracted by this might be complex valued. Okay, so after subtraction, because the low pass response is complex valued, because of that, when you subtract 1 with that, it's not going to have a pass band and stop band. Okay, so it doesn't work. This method doesn't work. So that concludes my my review for the midterm, and we've run out of time almost. So we have 2 more minutes. So we should get back to the students on the Nyquist frequency issue. Okay, so if Nyquist frequency is a term that confuses you, during the exam, please come talk to the TA. So we will, maybe not today, not right now, but let's take it easy. So we will, you need to discuss how to give to ask on some partial credits, right? So should we plan to handle that next week? Or when do you, no, you cannot. Next week, or what time do we handle this? 现在吗? You prefer to handle it right now? Okay, let's handle it right now. Okay, after if Nyquist frequency is why you fail that part, because you use a different definition, please come to the TA right now. Okay, thank you. That's it. Thank you for being here.